Let's talk more about electron delocalization and try to get to a point where we can recognize the patterns in which delocalization is going to be important. Your textbook lists 5 different patterns that you might see for delocalization. I am kind of using those 5 here. I'm combining 2 of them. I'm rephrasing a little bit. But here are the patterns you should look for to see when delocalization might be important. So the big ones are here. So the allylic system, that's what we went into detail on the last video. Allylic just means this 3-carbon chunk where there's a double bond, pi bond, between 2 of the carbons, right? So here I would call this a pi bond, and then I would call this the allylic position next to a pi bond. So here, in our last video as well, we talked about having 4 pi electrons that are overlapping each other. So again, you can picture all of these p orbitals overlapping each other. Here I've got 4 electrons in that system, a lone pair on this carbon and a pi bond here. And so I can think about those 4 electrons spread out over the 3 atoms. And so I can show that by showing different resonance structures. This double-headed arrow means that these are 2 ways of drawing the same thing. And to be really clear, this isn't bouncing back and forth, right? This is just 2 ways of drawing, representing the same thing. But note here it's pretty obviously a 50-50 mixture, right? Because they're just mirror images of each other. No reason it would be favoring the top or the bottom. But it doesn't always need to be that 50-50 split. So down here I've got a system where everything is neutral, right? I've got neutral oxygen with 2 lone pairs, neutral nitrogen with 1 lone pair. But I still have that pattern that I'm looking for. I still have a pi bond next to a lone pair. And whenever I see that system, 3 atoms, pi bond next to the lone pair, I have to consider resonance, right? So there is kind of a little bit of this character to it, where this oxygen has a negative charge and this nitrogen kind of has a positive-ish charge. And there's a little bit of a pi bond here instead of there. Again, these are resonance structures, 2 ways of drawing the exact same thing. This one in particular is really important for biochemistry. As you think about proteins, proteins are built from this unit. And the behavior of proteins involves having this pretty negative oxygen and pretty positive nitrogen as important parts of that system. Okay, so this resonance is super, super important to biochemistry. Here I have the same orbital system, but instead of having 4 electrons, I have 2 electrons. So instead of having a filled orbital with a negative charge, I have an empty orbital with a positive charge. So this picture applies to both of these columns, all right? And just like before, I can think about these 2 things as resonance structures, 2 different ways to characterize the same thing. It's not jumping back and forth. Again, why is this important? It's important because if I asked you, where's the positive charge in this ion, if you just looked at this picture, you'd say it's there. But that's not really accurate or helpful. The right answer is that positive charge is primarily spread out over 2 atoms, in this case equally. Here I've combined 2 different scenarios that your book lists. Your book lists a lone pair next to a carbocation, that's here, and a polarized pi bond, that'd be here. I think they're the same thing because in both cases we're talking about 2 electrons and 2 atoms. Right? So here, just like over here, I can think about a p orbital. So I've got a lone pair here, one of the lone pairs, not both of them, one of the lone pairs here, and I've got this empty orbital here. And so I can think about that lone pair sliding over to that carbon and making a double bond. If it does that, then that positive charge would go to oxygen because oxygen is giving up electrons. So again, these are resonance structures of one another. which of them is better, your book would say that this one is better because it satisfies all the octets. I disagree with your textbook. I think this one is better because carbon is not as electronegative as oxygen. So the atom on this molecule that is the most positive is definitely still carbon. Here, I've got a scenario that if I just look at the atoms, it looks really, really similar, right? Carbon, oxygen. The only difference is that here this oxygen has a bond, and here this oxygen just has another lone pair to give it a negative charge. Otherwise, it's the same. But in both cases, I can think about one of these lone pairs going and helping out its carbon neighbor. Its carbon neighbor is electron poor. Its neighbor is like, howdy neighbor, do you need some electrons? I can help you out with that, you know, just for a friend. So these two, again, different pictures of the same thing. What good is this? Obviously, this is a better representation, right? Everything is neutral, full octet, etc. But drawing it like the ionic form reminds us that that CO bond is polar. It has a positive end and a negative end. Could I break it up this way and just put that positive charge on oxygen and negative charge on carbon? Well, no, not if I want to describe reality at any level, right? That negative charge is not going to go on carbon. It's going to go on oxygen, right? So there are rules. When you're breaking up that polarized pi bond, get the polarity right. Then finally, our last video, we ended with this conjugated pi bond. So taking this idea of the overlapping p orbitals and just extending it as far as you want, as many p orbitals as you want to have lined up with one another. The most common way to do that is in this six-membered ring. As you're learning your molecule names, this is an arene, right? It has a special name because it has special properties. It turns out to be really, really stable, right? So here I've drawn benzene, the smallest arene, two different ways. And frankly, as a practicing chemist, my eyes just glaze over the difference. If you're coming to this new, you might pick up on that difference more readily. You might say that, hey, here the double bond is between 12 o'clock and 3 o'clock, and here the double bond is between 10 o'clock and 12 o'clock, right? So what's the difference between these two things? Again, there's no difference between these two. These two are resonance structures of another. If I were to look at the bond lengths, and you've done this in class, the bond lengths are equal. It's not 3 short and 3 long. It is exactly equal. All 6 carbon-carbon bonds are the same length, right? So one of these by itself is a bad representation of benzene. We need to remember in our minds that there are 2 ways to draw that, and both of them are equally good. Lots of people draw that with just a circle in the middle to emphasize how spread out those electrons are. Not a big fan of the circle, though, for reasons that'll be more clear once we really get into it. Here is another one where here I've got what looks like 4 atoms in a row with a p orbital, right? So I've got a pi bond next to a pi bond here. But I can imagine that all those 4 electrons are spread out with each other. So this is 4 electrons over 4 atoms. And again, it's got clear directionality. I want to put that negative charge on oxygen because oxygen is the most electronegative atom, and there's electropositive carbon. These are resonance structures of each other. And again, they help us explain reactivity. So it turns out that in this molecule, that carbon, 2 away from the ketone, is really, really electron poor. I can tell that both with IR and NMR, and I can tell that with reactivity, trying to make molecules from this. If I didn't understand this resonance structure, it would be really weird for me to know why is this more electron poor than this one closer to the CO, right? But having resonance structures, now I understand why this is so poor, because if I think about this as a conjugated system, the electrons are all flowing from here up to there. And finally, here we can think about really long extended. So here I've got 8 electrons over 8 atoms here. right? Notice this 9th atom really kind of isn't involved. There's no pi bond there. But all 8 of these pi orbitals like this, dig, are connected to each other. So here I can think about, again, resonance structures. I haven't broken it up in plus and minus because it seems kind of weird to break it up like that, right? Which one would get the plus, which one would get the minus. Instead, I'm breaking a bond in half. These dots are radicals, single electrons. So here I am taking one of these pi bonds and just sending one to the left and one to the right, right? Conjugated system. If we zoomed in, again, we would see that we might see these aren't all exactly the same length, but it's not quite as short, long separated as we would have predicted, because this is all just one big system. So these are the patterns that we're going to be looking out for when we're thinking about when our drawings are lying to us, when we have to think about electron delocalization or resonance. The big thing is going to be these allylic systems, allylic ions, negative charges, positive charges, or really any time I've got a lone pair next to a pi bond like this. Anytime I see a lone pair next to a pi bond, I'm going to have to think about resonance. Anytime I see a polarized pi bond, I'm going to think about that resonance structure as explaining why it's polar. And frankly, when I have a lone pair next to any C+, I'm thinking that lone pair can go over and help it out. And finally, when I have double bonds next to each other, alternating with each other, then I have this system. One time, and finally, when I have alternating pi bonds, like this, I can think about connecting, either spreading them out perfectly as in arenes, or at the very least thinking about that chain of pi bonds as one system that electrons can go back and forth in.